So now we deal in the zeroth law of thermodynamics, which is very simple and is very logical. I have shown here three systems, A, B and C. Okay. And the systems A and B are separated from each other by an adiabatic wall. Adiabatic means no energy can enter or exit from it, this wall. So this is a complete shielding, complete insulation between two systems A and B. Okay. And these two systems, as has been shown, they are in contact with third system, C, via a conducting wall. This wall is conducting. This wall is adiabatic. This wall is adiabatic and this wall is conducting. Now, what we do is that after this arrangement is there for sufficiently large amount of time, then we replace this wall, this adiabatic wall, by a conducting wall between the two systems A and B, and separate the two systems from the system C by a adiabatic or insulating wall. Then what happens? After a sufficient amount of time has elapsed, or when we think that we found that the states of A and B, they change no further. Before that, time has elapsed, they do change. And when they don't change, then we say that there is a state of thermal equilibrium, and they are in thermal equilibrium with each other, A and B. So we define zeroth law of thermodynamics as when two systems in thermal equilibrium with a third system separately are in thermal equilibrium with each other. Okay? Like if two lines are parallel to a line, then they are parallel to each other. That was told to you in your primary classes. Now this law, zeroth law of thermodynamics, incidentally, it was found and introduced by one Mr. Alec Fowler in 1931, who appears to be more of an author than a scientist or an engineer. Okay, in 1931. And by that time, thermodynamics was the established science, with first law, second law, third law, like this, that. It was fully equipped and a very strong system of macroscopic treatment of matter. So, intelligently, he called this as the zeroth law of thermodynamics. And when the two systems are in equilibrium with each other, then it does occur to us, we are bound to think there must be something which is common between these two. And that something we will see is what we call a temperature. So temperature is formally defined as a product of the thermal equilibrium of two systems which were in contact with a third system and finally evolved to be in thermal equilibrium with each other, So if the temperature of this is 30 degrees Celsius, the temperature of this one is also 30 degrees Celsius. If it is capital T, Kelvin, this is also capital T, Kelvin. Although Kelvin scale also came much after thermodynamics was established. So, as we saw in the system, if the temperature of the system ultimately TA is equal to Tc and the system B is Tb is equal to Tc, then of course TA is equal to Tb and the system are in thermal equilibrium as per the dictates of common sense. Okay, the only thing now remains is that the temperature has been formally defined in thermodynamics. Okay, now what remains is, which you will see, as to how the temperature scales evolve and the various temperatures can be measured quantitatively. To do so, we need to understand the concept of heat, internal energy and work. And doing so, we see that the temperature is a marker of hotness of the body. Okay, how hot the body is. And we have the notion that heat flows from a higher temperature, a body at a higher temperature to a body at lower temperature. But the flow of heat stops when the temperature of one system is equal to temperature of the other system. And that is what we defined as thermal equilibrium. Now let's introduce to you an intricate concept of internal energy. So today we know, as of today, not that time when thermodynamics was developing, every bulk system has a large number of molecules. And the internal energy can be said to be the sum of kinetic and potential energies of these molecules. What? The sum of the kinetic energies and the potential energies of all the molecules in the system which comprises several molecules. There is a big however. The however is that in thermodynamics, the kinetic energy of the system as a whole is not relevant. So for example, I have a system, okay, and the system is static, and then the system is made dynamic and the system moves. Of course, the system will have a mass, will have a velocity, will have momentum, and so associated kinetic energy. But this kinetic energy of the system, when the system is moving as a whole, is not at all of any importance in the science of or the art of thermodynamics. Therefore, we have that the internal energy of the system is sum of the kinetic energy plus the sum of the potential energy for the frame of reference. For the frame of reference relative to which the center of mass of the system is at rest. What is the center of mass of the system? At rest when the frame of reference is within that system. Okay. Now, we must further understand that therefore the internal energy includes only the disordered energy associated with the random motion of molecules inside the system. This is represented by the letter U, but we must bear in mind that this U, the internal energy, is simply a macroscopic variable of the system. Macroscopic, although we have tried to explain it to you with microscopic concept of molecules. But we must bear in mind that as long as we are doing thermodynamics, we consider the internal energy of the system as a macroscopic variable of the system. Now let me tell you that the internal energy U only depends on the state of the system and not how that state was achieved. The history of the achievement of the state is not important at all. So the internal energy is a function of the state described by specific values of pressure, voltage and temperature. And I repeat, not on how it was achieved. Okay? So in a gas system, what defines a gas system in the macroscopic way is the pressure, the volume, the temperature and the internal energy. And naturally in doing so we also invoke the mass of the gas. The gas has molecules. Random motion of molecules are there, and these motions, they comprise translation from one place to another place, rotation of the molecules, also vibration of molecules which contribute to the internal energy. Now let us discuss ways of changing the internal energy. Okay. So I have a system in which I have some fluid here and I have a connected piston arrangement here with pulleys to where I can put some masses over here. The other thing that we can do is we can use heat to change the temperature of the system. Okay. So the two distinct modes of energy transfer to a system to change its internal energy, they are heat and work. So in the first case, if I burn the heat here and give it a rise in temperature, then there is a energy transfer to the system, and the energy transfer is between the system and surroundings due to a difference of temperatures. Temperature over here and temperature over here are different, and therefore when I supply heat to the system, then the temperature rises, etc. Okay. This is one way. The other way is that, and we lower the temperature also, we can put it in a ice container or something like that. Still there is a transfer of the internal energy of the system. The other thing is that the work is energy transfer by raising or lowering some weight on this pan. If I raise the weight over here, then the piston goes up and there is a work done, and this work done results in the if I lower the weights over here, then what happens is the piston goes down. In both cases there is a change in the internal energy of the system. So by raising or lowering some weight on the pan, of course while we do so, the change in the temperature is negligibly small. Okay, so we don't consider that. So I repeat, there are two ways, one by means of heat and the other is by means of doing work. So heat and work are the two means by which we can change the internal energy of the system. Okay. Let's talk about the first law of thermodynamics. Okay. And in doing so, let us say that let delta Q be the heat supplied to the system by the surroundings, and delta W is the work done by the system on the surroundings. Okay, remember that. And that results in a change in the internal energy of the system equal to delta E. So, by common sense and by thinking about the law of conservation of energy, we'll say that the change in the heat is equal to change in the internal energy plus the work done. Delta Q is equal to delta U plus delta W, which is nothing but the statement of the first law of thermodynamics. Very simple. Law of conservation of energy. Well, so I can write this equation in another form, that delta Q minus delta W is equal to delta E. That is the change in the internal energy of the system. Okay. So let us have two states, an initial state and final state. Okay. There are a number of ways number of paths by which we can transform the initial state to final state. For example, let's take the case of gas. Gas is in a state P1 V1 and finally it goes to the state P2 V2. Now what can I do? I can change the volume from V1 to V2, keeping the value of pressure constant. So what happens? From P1 V1 it goes to P1 V2. Later I can change the pressure from P1 to P2 with no change in the value of, okay, so in the second stage. So the system goes from P1 V1 to P1 V2 and from P1 V2 to P2 V2. Okay. The vice versa is also possible. That first we change the pressure with delta V is equal to 0 and later on we change the volume with delta P is equal to 0. So these are the possibilities. Okay. This is how a change can take place, change of state. Okay. And now I must tell you that this delta U depends only on the initial and final states of the system, and not on the path. Not on the path. So the history is not important. How it has been achieved, how the value of delta U has been changed. Well, at the same time, this delta Q, the change in the value of the heat, and delta W may be path dependent. Not necessary that they should also be path independent. But the difference, of course, delta Q minus delta W, which is equal to delta U from this relation over here, has to be path independent. It will not depend on the history. Now let's take a case that if delta U is equal to 0, there is no change in the internal energy of the system. For example, in isothermal expansion of ideal gas, rarefied gas at low density gas, okay, so that ideal condition, which is normally ideals are never realized, so in that case, because delta U is equal to 0, so delta Q minus delta W is equal to 0, or we get delta Q is equal to delta W, no problem. If the system is gas in a cylinder with a movable piston, okay, the gas does work. And we can say that if the piston is moved, then there is a pressure multiplied by the area working for a distance, and that will give you delta V. So the work done becomes equal to P delta V. And therefore I can write the equation for delta Q from there as delta U plus P delta V. Now, to substantiate this argument, I'll just give you a small example of what happens if 1 gram of ice or water is converted to latent heat to 1 gram of water vapor. Okay. So as I told you, I'll just calculate the change in the internal energy of the system, and the system is very simple. I have 1 gram of water at 100 Celsius, and it goes from the liquid to the vapor phase, and the concerned latent heat is, we know, 2256 joules per gram. That is, for 1 gram of water, the delta Q is equal to 2256 joules. The experiment is conducted at atmospheric pressure, and at that pressure 1 gram of water has volume of 1 centimeter cube in the liquid phase and 1671 centimeter cube in the vapor phase. All these data are provided to us. Now we calculate the work done. Delta W is equal to P, which is the atmospheric pressure, into the change in the volume. The volume later here 1671 and 1 centimeter cubes. So when I put the value of P at the atmospheric pressure is 1.013 into 10 to the power of minus 5, and this we multiply is 1671 minus 1 is equal to 1670 into 10 to the power of minus 6 when I convert it to meter cube, etc. So when the proper units are taken, then we calculate that the value of this work done is simply 169.2 joules. And the change in the internal energy, if I subtract this value from this value, then find it is 2086.8 joules, which shows that because this is an actual calculation for the actual situation, we find that most of the heat which is provided to the system in the conversion from the liquid phase to the vapor phase is it goes into increasing the internal energy of the system. Next, we'll talk many other factors related with this. For example, the specific heats, the gram specific heat, the molar specific heat, etc., which we have done before also. But I'll do it again for you, and also that C2 minus CV is equal to R, etc., etc. in the next lecture. So, thank you very much.